Hello, friends. Today we're going to be studying trigonometric identities. So identities are two expressions that are equivalent to each other. Identity meaning they have the same identity, the same value. And buckle up. This is going to be a ride. The goal here is to try to understand what it is that we're doing. But there's going to be some things that you just need to memorize. And memorization is probably just what you need to do. And then associate it with the understanding that you have. Try to build the understanding as you go. So let's begin. Initially, we know that we have any kind of a point here. It's got the horizontal and the vertical. The horizontal we know now is the cosine value. The vertical is the sine value. But the thing to keep in mind is that this is a right triangle, and the hypotenuse of this right triangle is one. That's when we set out at the beginning of the unit circle. The unit is one, so it's a unit one radius circle. And so, because we know that about these values, sine and cosine, then this is true. Sine squared of theta plus cosine squared of theta equals 1. And so that's just the Pythagorean theorem, using what we know about the unit circle, sine and cosine values. And so this is what we call the Pythagorean identity for the unit circle. Then we can take this identity and we can manipulate it for other things. So for example, if we take this and we divide both sides by cosine squared, then what do we end up with? All right, so we take this, divided by cosine, divide everything by cosine squared. So sine over cosine, well, that's tangent, right? Cosine squared over cosine squared, that's 1 right there. And then 1 over cosine squared, well, 1 over cosine is secant. And so that's secant squared. And so here's another identity, another thing that's equivalent to the Pythagorean identity, and that might be useful depending on the types of functions that are given to us. And so what we end up with here is like this game of substitution, substituting this expression for this expression, um, and working from there. Also, if you were to take this and divide by sine squared, then you would end up with this. 1 plus cotangent squared equals cosecant squared. And so we have these three equivalent forms of the Pythagorean identity. Again, I would definitely recommend memorizing this one. But again, this, in terms of memorizing, just understand that it's the same thing as the Pythagorean theorem. And then these just derive from that with one simple algebraic step. I mean, relatively simple algebraic step, just dividing by sine squared or dividing by cosine squared. You get these alternative forms of the same thing here. Let's take another look. Okay, so if we call this, instead of calling this the vertical y, if we call it h, we can come up with an expression for what h is, because then apply the Pythagorean theorem, x squared plus h squared equals 1. Okay, and then if we solve for h, Pythagorean theorem, we get h equals the square root of 1 minus x squared. So now we have another expression for what h is. Okay, and then now we get to like sine and cosine and that kind of thing. So cosine of theta, cosine is adjacent over hypotenuse, right? So that's x over 1. That's equal to theta, right? Don't forget, right? X over 1, cosine theta. So then, sorry, cosine of theta is x over 1. So theta is equal to inverse of the cosine of x. Okay. Sine of theta is so h, right? The vertical, but the vertical now we've labeled as 1 minus x squared. So is the vertical over 1. That means theta is equal to the inverse sine of 1 minus square root of 1 minus x squared. But notice now this and this are the same, right? This is theta and this is theta. That means that these two things, inverse cosine of x and inverse sine of square root of 1 minus x squared, that those are equal to each other as well. And so we end up with this new identity. It's an inverse trig function identity. Okay. And so here it is initially. You could work the other way too. And instead of using h, the vertical, you can use the horizontal, and you can get it this other expression as well. And then, inverse cosine is the same thing as arc cosine. Inverse sine is the same thing as arc sine, etc. Okay, so these are the inverse trig functions. Again, the thing, memorize it. but again, try to work for the understanding. Go back through and review this and see, wait, how does that work? How did we come up with these things? So here's an example of something that you might see. The inverse function is given by tangent, f of x is tangent over cosecant. Rewrite this as a fraction involving only powers of cosine and no other trig functions. Okay, interesting, right? So tangent of x over cosecant of x. So what is that? Tangent is sine over cosine over, and then cosecant is 1 over sine of x. So this is sine squared of x over cosine of x. How do I get sine of x, sine squared, to be just in terms of cosine with no other values? Well, using the Pythagorean identity, right, which is this, sine squared of x plus cosine squared of x equals 1. Well, from this, I can get that sine squared of x is 1 minus cosine squared of x over cosine of x. And then we're left with that. So there is f of x just in terms of cosine and nothing else. You're going to see this kind of thing probably on the test. All right, sum identities, not SOME, some identities, but SUM, some identities, because we're adding together. So this is when we've got two angles that we're adding. So we're saying sine of this angle plus this angle. We're throwing more Greek at you. We've got theta for angle measurement, but also alpha and beta. I may have shown you phi for the phase angle before, right? But anyway, now we've got that's alpha, alpha and beta. And so we're imagining that we've got two angles that we're adding. So we're taking sine of the sum of those two angles, really making one bigger angle out of them. And so that's sine of alpha plus beta is sine of alpha cosine beta plus cosine alpha sine beta. Cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Okay, and so here they are, those two, but then you can also switch the plus and the minus, um, and then that determines where the pluses and the minuses are in the expression as well. But also the double angle. So what if alpha and beta are the same? What if alpha and beta are both equal to theta? In that case, you get the double angle identities, right? So there you would have, so if alpha and beta were the same, then you have theta plus theta, so that would be 2 theta, and then sine alpha, uh, or like sine theta cosine theta plus cosine theta sine theta, well then that would be the same term, and you could just add those. So that would be 2 sine theta cosine theta. Over here, if theta is the same, then you would end up with cosine squared of theta minus sine squared of theta. You'd get this. Okay, now we can substitute using the Pythagorean identity. Cosine squared could be 1 minus sine squared. So if you plug that in, though, then you end up with 1 minus 2 sine squared. Sine squared, like we saw before in the previous example, is also 1 minus cosine squared. So if you plug that in, then you get this. So it like multiplies because there are all these different things that we can plug in. There are a few basic ones that you need to remember, right? The Pythagorean identity, that's really the main one. The inverse trig identities, and then the sum and difference identities, because the double angle identities come out of the sum and difference identities, right, if you're trying to memorize the minimum. But then you've got to be skilled at plugging things in and working from there. Let's take a look at example 2. Which of the following is equivalent to the expression 2 sine pi over 14 cosine pi over 14? So immediately I look at this and I'm thinking, well, pi over 14 and pi over 14, that's the same angle. And I've seen that here in this kind of thing, right? So that looks like this, 2 sine and cosine there, right? So this is going to be sine of 2 theta. So what we end up with is, let's see, so 2 sine of pi over 14 cosine pi over 14. Using my double angle identity from before, this is now going to be equal to sine of, whoops, pi over 14. 2 times pi over 14, so pi over 7. Okay, for example 3, we have this function, and it's 4 cosine of 2x. Right, so it looks like I'm going to be using a double angle formula, but I'm going to isolate the 4. I'm going to bring the 4 out front because I want to look just at the cosine of 2x. Or what are the different things this could be equal to? Well, it could be equal to cosine squared of x um, minus sine squared of x. It could be equal to uh, 1 minus 2 sine squared of x. Or it could be 2 cosine squared of x minus 1. Okay, and so which of those looks like one of the options I have here? Because realize it would have a 4 in front, right? So 4 times each of these expressions. And it's going to be this one. 8 times cosine squared of x minus 4. That's that one right there. All right. Example 4. Which of the following is equivalent to the expression? Okay, so we've got cosine 8 over, or pi over 8, cosine pi over 16. And so we're going to be looking at an angle sum theorem where the two angles writing together are pi over 8 and pi over 16. So which of our double angle formulas has this kind of form? Cosine times cosine minus sine times sine. That's going to be this one right here, right? So I can rewrite, so what is that? Cosine of alpha plus beta. And careful with those negative signs, right? So cosine of pi over 8 plus pi over 16. So this is going to be cosine of 3 pi over 16. Okay. Last example. Example 5, they're giving us a triangle, and they tell us the coordinates are 5 and 12. This is a 5, 12, 13 right triangle. You can use the Pythagorean theorem, but if you know your Pythagorean triples, then this comes out pretty easily. Memorize the Pythagorean triples. Know them. Okay, so I want to know the value of sine 2 theta. Well, I know according to the identity that sine of 2 theta is 2 times sine theta times cosine theta. That's my identity. So I need to find what sine theta is and what cosine theta is. So this is 2 times, sine is opposite over hypotenuse, so 12 over 13 times, and then cosine is adjacent, so 5 over 13. And this turns out to be 120 over 169. So a lot of substitution, thinking through, things that trying to recognize these identities, what they look like, and then work backwards or forwards from there. Um, so thanks for watching. Don't forget to like and subscribe.